sklearn, linear model, logistic regression CV. Description. Logistic regression CV implements logistic regression with L1 and/or L2 regularization. It searches for the optimal regularization parameter C using cross-validation. This class is a wrapper around logistic regression that performs cross-validation to find the optimal C parameter. Inputs. X. This is a n samples, n features array, where each row represents a data point and each column represents a feature. It represents the independent variables or features used for training the model. Y. This is a n samples array, where each element represents the target variable or the class label for each data point. It represents the dependent variable or the class labels associated with each data point in X. Outputs. Core. This is the n classes, n features array, where each row represents a class and each column represents a feature. It stores the learned coefficients for each feature for each class. Intercept. This is a n classes array, where each element represents the intercept term for each class. It stores the bias term for each class. Steps. The logistic regression CV constructor takes several parameters, including C's, the values of C to be used for cross-validation. This is a list or array of possible regularization strengths to explore during the search for the best parameter. CV, the number of folds to be used for cross-validation. This determines the number of splits to be created when evaluating different C values. Scoring, the scoring function to be used for cross-validation. This defines the metric used to evaluate the performance of the model for different C values. Solver, the optimization algorithm to be used for solving the logistic regression problem. This parameter determines the method used to find the optimal coefficients and intercept. When fit is called, logistic regression CV performs cross-validation for each value of C. For each fold, the model is trained on the remaining folds and tested on the current fold. The cross-validation scores are used to select the best value of C. This involves choosing the C that leads to the best performance based on the chosen scoring metric. The final model is then trained on all of the data using the best value of C. Metrics. Accuracy. This metric measures the proportion of correctly classified data points. It's calculated as the number of correctly classified instances divided by the total number of instances. Precision. This metric measures the proportion of correctly classified positive instances among all instances predicted as positive. It's calculated as the number of true positives divided by the sum of true positives and false positives. Recall, this metric measures the proportion of correctly classified positive instances among all actual positive instances. It's calculated as the number of true positives divided by the sum of true positives and false negatives. F1 score. This metric combines precision and recall into a single value. It's the harmonic mean of precision and recall, providing a balanced measure of the model's performance. AUC. This metric measures the area under the receiver operating characteristic ROC curve, which plots the true positive rate against the false positive rate. It reflects the model's ability to distinguish between positive and negative instances. Visualization plots. Confusion matrix. This visualization presents a table that summarizes the performance of a classification model by showing the number of correctly and incorrectly classified instances for each class. ROC curve. This plot shows the true positive rate against the false positive rate for different threshold values. It helps visualize the trade-off between sensitivity and specificity, providing insights into the model's ability to discriminate between classes. Precision recall curve. This plot shows the precision against the recall for different threshold values. It helps visualize the trade-off between precision and recall, particularly in situations with imbalanced data. Fine-tune parameters. See the inverse of the regularization strength. A smaller value of C specifies stronger regularization. It controls the trade-off between overfitting and underfitting. Penalty. The type of regularization to be applied. L1 applies L1 regularization lasso, leading to sparse solutions, while L2 applies L2 regularization ridge, leading to smoother solutions. Solver. The optimization algorithm used to find the optimal coefficients and intercept. LibLinear is efficient for small datasets. LBFGS is suitable for larger datasets. And SAG is efficient for large datasets with many features. Multiclass. The strategy to handle multiple classes. OVR uses 1vs rest for multi-class classification, while multinomial uses a multinomial logistic regression model. Uncertainty methods. Confidence intervals. The confidence intervals around the predicted probabilities can be calculated to quantify the uncertainty in the predictions. This provides an indication of the reliability of the model's output. Challenges and fixes. Challenge 1. Overfitting. This happens when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1. If the model is trained on a small dataset with many features, it might overfit to the training data and perform poorly on new data. Fixes to challenge 1. Increase the size of the training data. This helps to reduce overfitting by providing the model with more data points to learn from. Use regularization techniques. Techniques like L1 and L2 regularization can be applied to penalize complex models and prevent overfitting. Use cross-validation. This technique helps to estimate the model's performance on unseen data and identify overfitting. Challenge 2. Data imbalance. This occurs when the classes in the target variable are not equally represented, leading to biased model predictions. Sample use case that resulted in challenge 2. If the dataset has significantly more instances of one class than another, the model might favor the majority class, leading to poor performance for the minority class. Fixes to challenge 2. Oversampling. This technique involves increasing the number of instances of the minority class by creating duplicates or synthetic samples. Undersampling. This technique involves reducing the number of instances of the majority class. Weighted sampling. This technique assigns different weights to different classes during training to account for the class imbalance. Challenge 3. Choosing the right hyperparameters. Finding the optimal values for hyperparameters like C, penalty, and solver can be challenging and require experimentation. Sample use case that resulted in challenge 3. Different hyperparameter values can lead to different model performance, and selecting the best values often involves trial and error. Fixes to challenge 3. Grid search. This technique involves evaluating the model with a range of hyperparameter values and choosing the combination that yields the best performance. Random search. This technique involves randomly sampling hyperparameter values from a predefined range and selecting the best combination. Bayesian optimization. This technique uses a Bayesian approach to intelligently explore a hyperparameter space and find the optimal values. Challenge 4. High dimensionality. If the dataset has a large number of features, the model may become complex and prone to overfitting. Sample use case that resulted in challenge 4. When dealing with high-dimensional datasets, the model may struggle to generalize well to unseen data. Fixes to challenge 4. Feature selection. This technique involves identifying and selecting the most relevant features reducing the dimensionality of the dataset and improving model performance. Feature extraction. This technique involves transforming the original features into a smaller set of features that capture the most important information, reducing dimensionality and enhancing generalization. Regularization techniques like L1 and L2 regularization can help to reduce the influence of irrelevant features and mitigate overfitting in high-dimensional datasets. Challenge 5. Computational complexity. Training logistic regression CV can be computationally expensive, especially with large datasets and multiple values of C. Sample use case that resulted in Challenge 5 when dealing with large datasets and a wide range of C values. The cross-validation process can take a significant amount of time. Fixes to Challenge 5. Use parallel processing. This technique distributes the computational workload across multiple cores, reducing the overall training time. Use efficient solvers. Selecting an efficient solver, such as SAG, can speed up the training process, especially for large datasets. Reduce the number of C values. Limiting the number of C values used for cross-validation can reduce the computational burden without significantly affecting the performance.